Thank you. First of all, folks, let me say thank you for your service. I just looked at the calendar and it reminded me that today is December 7th, obviously a very noted day in history. I just wanted to say thank you, appreciate what you do, and prayers will be going out to those folks today. My name is Daniel Barrios. I've been in this industry since about 1987 or such. The first thing I want to tell you is every time one of these bios come up, please hang on to my email address, hang on to my phone number. I have gotten calls maybe a year or so even after a presentation just for clarification. Please reach out to me. I enjoy doing that, and I welcome your comments. So this is the basic portion of automatic transfer switches. When we look at a transfer switch, we're going to look at the purpose, the definition, codes and standards, typical installations. These things, some of those will just be inherently understood. Some of the codes and standards and some of the definitions I would like to deep dive into so that you have a very clear understanding. When we look at the automatic transfer switch operation, there is a power panel, there is actually a controller, and there is a user interface. Let me make one clarification to you. This is not supposed to be a sales pitch for ASCO or Schneider Electric. Unfortunately, because I work for ASCO Schneider, the pictures that are in here are of ASCO products. When we go through this, we will discuss the differences. I apologize for that, but we keep trying to get these updated with other manufacturers. There are other major manufacturers of transfer switches, Russ Electric being one, who is owned by Siemens now, GE Zenith, which is now owned by ABB. ASCO obviously is owned by Schneider Electric, and then you have some of the generator folks, Kohler, the folks who provide generators also provide transfer switches, and Cummins provides a very good product also. So when you look at it, we're going to look at a few things, and a couple of these you are very seriously going to get tired of hearing me use a phrase such as withstand and close on. We'll get into that. Now, typically, as we make these presentations, our audience is a little vast. Sometimes we have consulting engineers, sometimes we have technicians. So when we're dealing with the consulting engineer or when you're looking at the application of a transfer switch, you need to know how many poles. What do I mean by that? If it is a 3-pole system, a 3-phase wiring, you obviously have an A, B, and C phase. You must have 3 poles that transfer. However, if you're carrying the neutral through that transfer switch, it may need to also be switched. We will cover that, and therefore you have a 4-pole transfer switch. When you're looking typically at single phase, that typically is a 2-pole transfer switch, 2-pole, typically 240 volt here in the United States. I understand this audience here is Hawaii and basically the West Coast and such. It is very important to know the voltage that we're looking at. Many products, and we're going to touch on one of the slides, is what's referred to as a safety switch. It was sort of used as a manual transfer switch before. It is still popular doing that way, but all of those products are rated for 600 volt. Anywhere from 120 to 600 volt is that class of product. In sales, we'll have people call us and tell us that they want a 600 volt transfer switch. Well, typically in the United States, we do not use 600. We use 480 volt. So you need to know the application voltage that you're using. Current, obviously, we're going to touch on that, but current is dictated by the upstream overcurrent protection device, whether that be a fuse or whether that be a circuit breaker. If you have an 800 amp circuit breaker, you must have at least an 800 amp transfer switch. I cannot legally put a 600 amp transfer switch labeled that way. I cannot legally put that in the circuit if it is protected by an 800 amp upstream device. When you're looking at the different methods, the most common one is what's called open transition. That is a term called break before make. It is either typically connected to your utility source or a standby generator of some type. However, when you're doing that switching, even if you're going back to the utility once it has returned, There will be that momentary blink of power as you open from the generator and you close to the utility. To answer maybe your question on that, that typically is no more than about 6 to 10 electrical cycles. It's very fast, but it does blink. A delay transition switch, other names are called that. It may be a neutral position or it may be a center off. Several manufacturers do that. The delay transition switch is that it will open a hot source and disconnect both services before it connects to the second service. Why is that? If you have a large motor of some type, if you have some type of an industrial process or so, you don't want that switch to transfer as quickly as an open transition. You would want to open the power, let the motor wind down, and then at some point, whatever that constant may be, it may be a few seconds, it may be 30 seconds or so, then you will re-energize that. Another application of that is that when you are dealing with a UPS, uninterrupted power supply downstream, many times they would rather see you delay that transition, break the first source. The UPS will acknowledge it's lost power. It'll go into its mode with the batteries. Then you close back to the other source and it returns to feeding the power through the utility side. A closed transition switch is an interesting product. To make a comment, it was originally designed for the FAA for runways. And one of the reasons is it is a make before break. If you are going from a hot source to a hot source, there's an overlap time, typically no more than 100 milliseconds. There's an overlap time where you basically have closed your utility to your generator and then opened the source you're leaving, and therefore your downstream load never sees an outage. Why the FAA? I've had two explanations. Number one, your radar does not restrike because you've had a blip. Runway lighting does not have to restrike. Just a parting comment. The other source here is when you look at an automatic transfer switch, there is also what is referred to as a bypass isolation switch. We've got some good pictures of this. Why is that? Well, number one, if you want to exercise, if you want to test your transfer switch, many times you need to notify all of the loads downstream that you are going to have a momentary outage while you test or maintenance that transfer switch. In a bypass isolation switch, there is a second set of busway that you bypass to normal. Now you can remove the automatic portion of the transfer switch to test it or maintenance it, put it back in, come off a bypass, and nowhere downstream has anyone known that you were in that transfer switch doing maintenance. Many of the data centers, and in fact, in some portions of the National Electric Code, NFPA 70, in the National Electric Code, I believe in California, they are now mandating that at least within emergency systems and hospitals with life safety requirements, that they are requiring a bypass isolation switch. And we'll probe into that a little bit better as we go into this presentation. So what causes an interruption? You can read that. One of them is probably not on, yes, it is on there, earthquakes. But in our case down here, I'm in the Mississippi Gulf Coast area. I'm over in Texas now, but lived in New Orleans. Obviously hurricanes. And in fact, some of California's had some hurricanes this year. But in this case, even including a human error can cause a interruption in your normal power coming in. Many times it really is just because things are not maintenance. It's not maintenance because no one wants to have the downtime while you're looking at your electrical system. Obviously, you can read some of these other reasons where a interruption in power may occur. So when we look at a transfer switch, the simplest one is this open transition. There is a single operator. Now, when I say operator, you will see that it describes that ASCO uses a solenoid. Obviously, this was taken from one of our presentations. Some of the other manufacturers use a linear motor. In either case, it is a means of moving the contact off of one source and moving it to the other source. In this case, it is a conventional two-pole switch. The thing also is that it is a normal power seeking. That's a good walk away comment. A typical open transition switch transferring between utility and a standby generator would prefer to be connected to the utility. What does that mean? That means that should the utility go away, you go to the generator. When that utility comes back, and there is a timer typically set for 15 to 30 minutes to be sure the utility is back properly, it will retransfer back to the normal source automatically. As you see down at the bottom, the smaller the switches, switches are made all the way down to 30 amps, and they go all the way up to 4,000 amp with many of the manufacturers. And that solenoid driven operation, that linear motor driven, is usually done within 6 to 7 electrical cycles. So you need to be sure that you're in phase. One of those is many of the manufacturers offer what is called an in-phase monitor. It will look at the two sources and it will see when it is basically in phase. It will anticipate that zero crossing and it will transfer with a minimum of difference in shift of the power so that you don't do damage to any motors or such. Give you an illustration of that if you're looking at it, and we're going to talk about this in closed transition, but if you have a blinker on in front of you while you're at a traffic signal, and you put on your blinker, you'll notice they blink out of phase, and then for a couple of times they hit at the very same time, and then they get back out of phase again. This is what an in-phase monitor is monitoring. Can we look at that? Can we anticipate that and make the transition while we are doing that? Now, when you go to a delay transition switch, obviously I've made the other comments, a center off, neutral position. There is more components. Now you have two operators to operate the normal set of contacts and the emergency set of contacts independent of each other. There is an intermediate position even on a hot to hot. And that is, as I say, for the back EMF to wind down. If you go to the gym and you look at one of those large fans, if they turn the power off, you can see how long the fan continues to cycle. Usually a 5 to 0 minutes to 5. That is a user selectable. In every case of the manufacturer, you can go to their controller and you can typically dial each of these that we are going to discuss. The timers are such that you may want to do. Typically, you're not waiting 5 minutes. On wastewater, water treatment plants, they may delay a long time because it's not critical that they're back on within 10 seconds. A life safety switch, according to the National Electric Code, if it is an Article 700 installation, we'll touch on those. If it's an Article 700, those life safety loads must be re-energized within 10 seconds. In the case of skimmers or bubblers or such, typically in a water treatment plant, if it waits 30 seconds to a minute or so before it's re-energized, it typically is a safer transition and not damage any of the equipment. And this is not any type of replacement for any of the other inputs. It will not alleviate transformer inrush. Transformer inrush will happen when you re-energize. However, all transfer switches are aware of that. They will ride through that momentary surge of power while that transformer is taking a few cycles to be re-energized. Now, the closed transition switch, as I said before, again, you have two operators that work independently, but it is a hot-to-hot transfer. This is very good if you are trying to test in a life safety situation, if you're trying to test something in a data center where you cannot have an interruption. This switch, the only problem that I will comment to you is that you need to discuss this. You folks may not fall into that, being Navy, but when we are talking to commercial installations, you need to know if the utility will accept the closed transition switch. They may want to have additional discussion or stipulations. In the case here down in Houston, Texas, we have to prove that if the transfer switch is connected to normal and you attempt to transfer to emergency and normal does not open, you have to reopen emergency and you have to trip a breaker within a half second. and that will typically have to be demonstrated and proven to the local utility company. Did I hear someone ask a question or so? Okay. So moving on, wire transfer switch is needed, and trying to get that out the way, to help prevent accidents, panic, loss of life. Typically, these two, the loss of life is really due to, as we've stated, hospitals or such, getting people out of the building when you have a large arena or such. The second one is even driven stronger by the data center people. Their loss of revenue can be a large amount of money per second, per minute. You need to comply with codes and standards. Now, when you look at that, and we're going to go through this, we are going to touch on a group of standards that is referred to as NFPA, the National Fire Protection Association. And those codes are typically used in many applications. When you look at standards, excuse me, the standards may be how it's manufactured or such, and how you have to get a UL label on your product or so. The other point to it is, though, that when you look at government regulations, specifically, you folks may have more stipulations, but within something like Los Angeles or so, the county may have a certain number of regulations, but within the city of Los Angeles, it may have stronger. I know Chicago is that way. Inside the city limits of Chicago are stronger conditions than even within the county that it resides in. Whenever two or more sources of power are utilized for essential electric loads. You know, that's almost a misconception now, because you think of backup power, and backup power is for things like hospitals, arenas, data centers. But, you know, I don't know that you can go into any facility now that does not require backup power. One of the ones down here in the hurricane prone area are grocery stores. If a grocery store loses power, number one, obviously food spoils, but number two, you can't even get through the registers. Now, in the state of Florida, Florida has mandated now that all convenience stores, whatever you refer those to those as, 7-Elevens or such, they must have a means to connect the standby power generator. Why? They had gasoline to pump for people to evacuate, but they had no power. So now that is at least within Florida, and I believe other states will take on that. That says no, no, no. You need to have the ability to pump gas to continue the evacuation in the case of a national disaster. Oop, why am I? There we go. So this is what I'm getting to here. If you can just take a look at this, this may or may not apply to some of what you folks are trying to understand, but these are all articles in the National Electric Code. That National Electric Code is NFPA 70, NFPA 70. When you look at a 700 article, that's an emergency system. You must have a permanent generator. When you look at a 701, that is legally required. There are different stipulations to that, okay? Optional standby, believe it or not, is what a data center falls into, but obviously those people, you know, have permanent power that needs to be backed up with generators. And then lastly, the one that was added, a few editions of the National Electric Code. Right now, we are up to the 2023. 2023 has been published. It may not be adopted in your area. The previous one was dated 2020. The one before that was 2017. In this case, the 708 was added. These are critical operation centers, and that's your 911 call centers, your fire dispatch or such. Those have now been added that you must have emergency power. Again, though, even though you may have an office building, if you have all of your accounting, your data center or such, you would require to keep your business going, even under optional standby, that you can have power. In Article 700, you notice that the emergency systems are designed to automatically supply power. As you can read, the emergency system may provide power for ventilation. That's a very good comment. If you are a high-rise type building and your exit is to go down the set of stairs, obviously not using the elevators, those corridors need to be evacuated. They need to be ventilated so that it's safe for the people to evacuate through that area. An industrial process where current interruption would result in serious life safety. One of the applications I did several years ago was with Intel. They were over in the Arizona, New Mexico area, and they had a certain amount of seconds before the vapors of manufacturing the chips were actually lethal to them. So you need to look at all of this and what is your installation? Typical installations include not only healthcare facilities, as we state, but hotels, theaters, as you can read those. Many times now, you also have to look at, in the case of what is a last resort. In the case of a hurricane or an earthquake or a natural disaster, many of the schools now in this area is a shelter. So that shelter needs to have backup power while you evacuate all of those people to that condition. Now, when you look at legally required, automatically provide power to selected loads other those than classified as emergency. We have covered emergency. Emergency is life safety and critical typically. Now you're under this legally required, and trying to get rid of this little bar on top of my head. So the power interruption of these loads could create or hamper the rescue of firefighters. Typically, typically installed to severe loads such as heating, refrigeration, considering smoke, ventilation, and such. Legally required. If you have one of those facilities that falls under that guideline, you must have a standby system, a backup system. Now you go to an optional standby. Standby system is optional when you do not have either an emergency or a legally required standby. And these systems are to protect the public or private facilities. And the loads can be powered by either a permanently installed or a portable generator. And we will touch on those. Many of these facilities, though, still at least some type of permanent backup. Typical facilities include industrial and commercial buildings, farms, convenience stores, etc. I will try not to read slides. Just every now and then, there are some good comments pointed out in here. The critical operation centers, as I said, it was intended for Homeland Security. These are as stipulated in the third paragraph. These were added. Part of the problem was that we had a bad communication scheme, even here within Houston, Texas, Harris County, that the two systems were not compatible with each other, meaning the police and the fire department. So they had to get back in there. They had to get their two systems aligned so that they would stay both up, but also was able to communicate. As I said down at the bottom, so many of the schools in these areas now are storm shelters, and you need to have that available. Another point to that is that in many schools now, which are nice, much nicer schools than I went to, there's several floors, maybe two or three, so there are elevators involved. And obviously, because of handicap, don't mean to say that in a rude way, I'm sorry, the ADA, the Disabilities Act, you need to have those type of facilities where the elevator is available to evacuate those people requiring an elevator. So if you look at it, let's go a little bit better. Those, I'd like you to know those. If they're applicable, fine. I wanted you to understand those. The reference it goes back to is the National Electric Code. So the definition of a transfer switch is a device which transfers electrical loads to two dissimilar sources. Typically, it is a utility and a standby generator. However, many industrial or commercial applications may have two utility feeds coming in. There may be a utility A and a utility B. When one substation goes down, you simply transfer over to the other one. We'll discuss that a little bit different because you may want to select then which one you stay on. But typically, this transfer switch, the simplest one, is between your normal power source and your emergency backup. Now, we look at UL 1008. You're going to see some type of references to UL. What you have when you look at a transfer switch, they are manufactured under a set of NEMA or some type of manufacturing code. When you look at UL, then you have to send your product to UL, Underwriters Laboratory, and you need to explain to them how you are going to operate this safely. In the case of transfer switches, ASCO, Russell, Zenith, Cummins, Kohler, Generac, all of those, they typically fall under the UL 1008. Therefore, they are a transfer switch for emergency systems. We're back to Article 700 again. That automatic transfer switch is covered by these requirements. It automatically transfers and it automatically returns to the normal. As I stated, it is a power seeking. That is a typical automatic switch. When you look at a non-automatic switch, the power is going to go out, and yet someone has to go and initiate the transfer over to the other side. And then when it comes back, you have to reinitiate the power back. Why? Well, you may be in the process of doing something, the utility is back, you want to wait for that process to run or something, the change of a shift or so, before you would then do the retransfer back to your normal power. So when we look at a transfer switch, I'm going to state this now, what you are looking at is a typical ASCO product. Within the box on the left side, these are contactor style. ASCO, Russell, Zenith, Eaton, I didn't mate those. Cummins, many manufacturers use a contactor. There are some manufacturers, Eaton being one of those, Eaton Cutler Hammer, that still offers a circuit breaker type. 2 circuit breakers that will transfer between. In either case, on that left side within the can is the transfer mechanism. You see the little umbilical cord, the conductors, and that goes to the black box. In our case, that is our controller. When you open a transfer switch of other manufacturers, it may look different. It serves the same purpose. The brain is that black box. The brawn is actually the transfer mechanism mounted within the can. It's electrically operated. This one is the simplest operation because it only has one mechanism. It will move all of those, all 3 poles at the same time. When you look at a manual switch, and this is a little bit older picture of it, but a manual switch, you physically have to walk up. You'll notice there is no control panel. It is a very simple product, and you switch it from one source to the other source to feed your load. Why? Well, if I'm a small municipality type water plant and I have 3 sites, but I only have one roll-up generator, I don't have anything to transfer to until I roll my generator up, connect it, and transfer it over. So you may just use a manual transfer switch. The other one now that we're going to look at is that if you were back to the same thing again, if you have an Article 700, an emergency system, and you have a single generator, one generator backing up an emergency system, now you're required by code to have the means of rolling up a portable generator should that permanent generator be unavailable down for maintenance or such. And that would require some type of a manual transfer switch with what's referred to as cam locks to temporarily connect that roll-up generator to. When you look at what UL looks at, we're looking at construction requirements and all of the performance requirements. A couple of those that I want to touch on is the temperature rise. You will see that when you read the UL definition, there is only a certain amount of temperature rise on those contacts as you're flowing that much power through the transfer switch. The bottom one, you're going to hear me throughout this entire presentation, is withstand and close on. I'll give you the preface to that. The transfer switch may be a 600 amp rated transfer switch. That's what's going to pass through it typically. However, if there is a short downstream, depending on how close you are to the utility transformer or such, you may have an excess of 30 to 40 to 50,000 amps of fault current that will flow through that switch instantaneously. Typically, we're looking at no more than 3 electrical cycles. That's the withstand and close on that we'll touch on. So you may have a 600 amp switch, but it may have to endure 50,000 and not burn the contacts closed. It must go back to operation and such. We will keep continuing to discuss that. Another type is a lot of residential people use this, kind of a walking beam. If you look to your left side there, you'll notice also this one now is listed UL67. This is not intended for an emergency system. UL 1008 is. This is a simple way. When you flip that little walking beam, you must open one breaker before you can close the other breaker. Westinghouse originally had a design like this. Eaton Cutler Hammer had that switch available for a long time. I do not know if they've gotten away from it. It is a very simple means of doing that specifically in a residential application or so. A manual throw transfer switch. This is what I'm referring to. If you look at that, this is what typically had been specified as a manual transfer switch. This is actually what, when you look into your electrical components, this is actually a safety switch. Now, that safety switch can either be fused or non-fused. And what it is rated from 30 amp up to 200 amp. You'll notice this one now is listed under UL 98. And it is, you can use it, but again, it's not acceptable in an emergency condition. This is where under an emergency installation, Article 700, this one here is where we typically fall into the problem. This one is rated 600 volt, meaning anywhere from 120 to 600 volt can be passed through this product. When you look at it, one of the other things that you folks may run into is an AHJ, the authority having jurisdiction. In the case, many times that is your electrical inspector. In the California area, there is what's referred to as OSHPOD, and that is part of the hospital requirements that they are the authority having jurisdiction. Throughout some of the other areas is another hospital organization that will oversee things. But you need to know who it is. Is it the county? Is it the electrical inspector? Is it OSHPOD? JACO, the Joint Commission, is the one down here through many of the other states. JAHCO, I believe it's referred to, and that's the Joint Commission, specifically under hospital operations. But you need to know who is going to inspect your installation. They have the final say whether or not you can then use it, or they're going to red tag it, and you cannot put that into operation. You'll notice the two labels specifically state whether it is an automatic transfer switch or whether it is a non-automatic transfer switch, and they will specifically look at that under your installation application. Just a slide for you to walk away with, but you'll notice all the way to the left side are manufacturing. Going from top to bottom, you'll see that UL or ANSI and such, I should say, ANSI, many of those are how you manufacture it, how you construct it. UL and many of these others, CSA is the Canadian standard. EGSA is obviously the Electrical Generating System Association. ISO and ISE are those standards. IEEE, NEMA, and there is your NFPAs. Number 20 is for fire pumps. 70 is for your National Electric Code. 99 and 110, one of those is for healthcare, and the other one is for emergency systems. Just be aware of them. If you're doing an actual installation under that 99 or 110 application, healthcare or emergency systems, when you put that standby generator into operation, it is specifically stated how you need to test it. Usually that is a 4 to 8 hour load bank test before you can then commission that generator in order to be used as your backup power. Non-automatic transfer switches, obviously residential, convenience stores we've talked about, water treatment plants, small office buildings, and I believe I'm going to remove the wireless cell sites because by today's standards, you require those to be in an automatic situation. Automatic transfer switches, some of these are obvious. Telecom, banking, large office buildings, airports and such. But this is where an automatic transfer switch, police and security systems obviously are in that list. Pushing on a little bit more, again, looking at a contactor type transfer switch. On the left side, you will see the transfer switch mechanism. Notice two things. Number one, if you can see it, those silver are the lugs. You will notice that there's two of them facing up and one of them facing bottom. One of the top is typically the Emergency or the normal. The other one down at the bottom is the normal or the emergency. The middle one is the load. So that transfer switch transfers. When you are looking at this, many of those configurations can be changed. You can put emergency out the top, you can put it out the bottom, you can put load out the top, load out the bottom, but the emergency and the normal must be opposite of each other just by the way the contacts move. The controller, the CP, is the brains, and we will deep dive into that with some of their other functions that is in there. Many other installations. This one here is just typically a NEMA 1 installation. It's put inside a building. If you're not familiar with those, NEMA 1 are indoor. NEMA 3R typically is outdoor, drip proof. NEMA 4X will be stainless steel. NEMA 7 is explosion proof, which typically these products do not comply with an explosion proof installation. In this case, this is more of a secure door. If you'll notice, if you close that exterior door, no one can get to the control panel. No one can inadvertently change anything. Where are these used? We put these in a lot of prisons, facilities or such. Also, one of the things that came up here in the Houston area was they were starting to add backup generators to the DPS, the Department of Public Safety buildings. Well, in doing so, they had to put the switch outdoors because they have no more room in the building. They would like a secure door type enclosure that's behind a chain link fence that no one can mess with it inadvertently. Also, the one on the right, that is a stainless steel enclosure. And those can be either 304 or 316 stainless. Why? Many of these go onto the Mississippi Gulf Coast, possibly out in your area also, and the salt conditions just absolutely destroy a painted steel enclosure. Very expensive, but for the purpose, water treatment plants anywhere that has caustic fumes, typically we will see an installation of a stainless steel enclosure. Looking at the opened transfer switch, the automatic transfer switch, this is sort of what we go through. The current carrying is that transfer switch, that brawn. To detect the power, that is in the control panel. To initiate the transfer actually occurs with the mechanism, the contactor, sensing normal power back as part of the brain. Retransferring is the transfer switch, whether it's a contactor or such. And then lastly, the withstand and close on is a function of the material used in that manufacturing of that transfer switch mechanism. So look at this just for a minute. Detect the power failure. Many of the manufacturers use a relay that as long as the utility power is available, that relay is energized and it will open a set of normally closed contacts. When the utility fails, that relay drops out, it closes the contact, and that's what completes the circuit from the controller on the generator set through the transfer switch back to the controller. Typically, that's a 24-volt system that you'll have the voltage on one side of that contact. When you close the contact, the 24 volts returns back to the control panel, and that's what initiates the starting of that generator set. Those are where we are looking at. We kind of ran through those. We'll look at these. It's a solenoid or a motor mechanism. Now, there's another thing. You will notice there is what's referred to as a main and arcing contact. I always use the same illustration for those of us who remember the old black and white horror movies. They always had a set of wires, kind of looked like rabbit ears from a TV, and you'd see the arc jump, and it would go up until it dissipates. You'd get the that's called the Jacob's ladder. Why do I bring this up? The arcing contacts serve that purpose. When you start to move the transfer switch off of a connected, energized load, the first thing that opens is the arcing contacts. That's where that arc is going to strike until it becomes too far apart, just like on the Jacob's ladder, and that arc will dissipate. The arcing contact opens first before the main contacts, the current carrying, which we should have a better picture of, before those open, and the arcing contacts and the arc chute basically absorb that arc and distinguish it. So it is the arcing contact is a little bit of a sacrificial device. so that your main contacts are not damaged during typical transfers. We will state mechanical lugs. That is what typically you see on a set of transfer switches. Those are the ones that you put the conductor in there, you take an Allen wrench and you screw it down. The other ones that can be, many of the consulting engineers require what is called a compression lug. It is specific for that conductor size, a 350 MCM cable. It's crimped on and then bolted. The other one, meaning a bus stab or bus bars, if you're putting this transfer switch into a motor control center section, in lieu of cabling, you may just simply bus across out of the transfer switch onto the bus of the motor control center. When you look at the control panel, it does all the monitoring we discussed, the time delays. Any transfer switch that you have at your disposal, whatever manufacturer it is, I suggest you find out what controller it has, get a copy of their brochure, their literature, their operating, and it'll tell you this timer can be from 0 to 5 seconds. This one can be from 0 to 60 minutes or such. The enunciation and control, all of those things come out of that master, that controller, and it may be something that on your site you may want to know. Is power available? What position are we in? You know, is there a problem? So all of those come out of that controller. To give you a better picture, when you look at this, what you'll see is, looking on the left side, that's a transfer switch operator that drives the operator linkage below. Okay, if this is a open transition single operator, there is a piece of bar that's connected so that the top one moves and it moves the bottom set of contacts at the same time. You'll notice that those terminals at the top, as I said, they're kind of goofy looking. They sort of have they look like a clover in some respects, so that you can either put two of one size cable or one large cable. Those are very well defined. You can look at the mechanical, the installation drawing of all of your transfer switch manufacturers, and they will specify the range of conductors and what type of terminals they are providing. These main contacts, they're sort of like piano keys. They are independently floating. It's not just a standard solid piece of metal. That way, as there's wear and tear, they sort of are self-aligning and they stay connected. The main contacts we've talked about, the arc chutes, you see a little better picture of those. That is where that arcing contact is extinguished. And the power poles is so that we don't have someone inadvertently touch live equipment. Obviously, you're not supposed to open up a energized piece of equipment any longer that without proper PPE, your personal protection equipment. So you look at it here, the transfer switch operation, this is sort of just a breakdown of it. The way it goes is that solenoid, when it drops the SE to the ER, that's dropping out the normal power and energizing the emergency power. It will move that solenoid and it'll only be energized during the transfer. And what that'll do is that will then move, in this case, that round momentum as it comes around to top dead center. It'll de-energize the solenoid, and that's what completes the movement from the normal source to the emergency source. The switch is always powered by the source which it is going to. So what that means is, if it's connected to normal and for some reason your emergency system never comes on, that switch is going to stay connected to normal. If you're connected to emergency, it will stay remaining connected to emergency, obviously till the utility comes back. Let's touch on one other point. These products are mechanically held. They're electrically operated, but they are mechanically held. Whereas the lighting contactor is electrically energized. When you lose the power, a typical lighting contactor will drop out and the lightings will turn off. In this case, once you make the transfer, irrespective of what manufacturer we're speaking of, it will maintain connection even if both sources go away. It is not relying on any power to stay in that position. So you look at the controller on the left side, and that's what I'm pointing out. The time delay to transfer to the alternative, the time delay to start the engine generator, typically that is set at 1 second. You don't want to set it at 0 because then every little blip would start your generator. Typically, you have it at 1 second, even under an emergency situation where you must be re-energized in 10 seconds. Generator sets will ramp up tremendously quickly, and they will re-energize the power within 7 to 8 to 9 seconds or such, re-energizing the life safety. The rest of them can be energized, your emergency and your criticals can be energized after that 10-second rule. But each of the things on the left are the controller, and they are stipulated in your operation manuals what type of timers you can do. On the right side, obviously, is the transfer operator, as we've talked about, being whatever type it is. So when you look at it a little bit better, that's a good blow-up view of that one. And at least in the case of an ASCO controller, this is what the module looks like. And therefore, you'll notice now that there's an LED screen that is user-friendly and such. And that's where you will dial through it to put all of your timers and such into. ATS control design, microprocessor. Very quickly, we used to have relays and such that was a little more sloppy, but nowadays these things are at about 0.25% accuracy. Source monitoring, time delays. When you look at pilot lights and such, some are standard, and then auxiliary contacts, some are standard. They will tell you what position you're in or such, but if you need to know something else, you may have to have an additional accessory to add those contacts. An example of that is that typically with a transfer switch, you will have a switch position set of lights. We're going to see one of those shortly here. And you will also have a set of contacts that will tell you whether you're connected to normal or emergency. You may want to know that at your control station. However, you will have a set of lights to tell you that either your normal or your emergency is available, but you will not have the auxiliary contact stating that unless you pick that up. We can touch on that as we go through. If that does not make sense, we'll cover it a little bit later. Methods of operating, obviously we've talked about automatic and we've talked about manual. There is also a remote test switch. Many times you may want to be sitting in your control room. You can send a signal, close a contact. It will start your generator. It may start it and just run it. It may start it and also transfer it. So you have some capabilities without having to walk out to the transfer switch or having to walk out to the generator set out in the yard. So the automatic transfer switch, it looks for source. It does look for under voltage as well as over voltage. It'll look for single phase conditions, voltage unbalance. Phase sequence is very critical because if you've had some maintenance done while the utility is doing something or you've done something to the generator, when you reconnect those two loads, you want to be sure you're in the right rotation with each other. Most ATS controllers do not monitor current. We are only typically looking at voltage and frequency. Those are the two parameters required in order for a transfer switch to transfer. If you want to know metering capabilities such as amperage, kW, kVAR or such, you may have to pick up an additional device such as a meter of some type. The other overcurrent device, let's talk about that. We are not the overcurrent. We are not the protection device. We are expecting, we are requiring that upstream overcurrent device, as we stated, whether that be a fuse will typically clear very quickly within maybe a number of cycles, quarter of a cycle or such. In the case of a circuit breaker, you may be somewhere connected for anywhere from 3 and nowadays all the way out to 30 cycles. Transfer switches of a certain manufacturing design, several manufacturers offer those, are capable of withstanding a fault of all the way out to 30 cycles. A half second, that's an eternity in the electrical world. But if the fault where they're showing you that little X down past the transfer switch, we are expecting the circuit breaker from the utility feed coming in to clear. We're going to touch on this again, but withstand and close on. So we open that breaker. We start the generator and we transfer the switch to the generator power. I'm still closing back into that fault. That's what's referred to as withstand and close on. I'm going to close, the fault is still being fed, and I need to have my circuit breaker from my standby generator set open. That's what needs to be considered. Time delays, momentary. We typically set that at 1 second. In doing so, we're going to wait for that power. That's what I stated there. You see the engine start contact. It's a relay that is normally energized. When the power is lost, it closes that circuit, tells the power to go to the generator set and start it and make the transfer to emergency. A neutral or normal to emergency delay timer allows the emergency source, voltage and frequency to stabilize and enable before you transfer the load. Whenever you transfer a load, if you look at a transfer switch and it's a 600 amp transfer switch load, when you go from one source to another source, it is going to transfer everything, that complete block load, to the source you're transferring to. Okay? What do I mean by that? Your generator set, if you've been through that, when you drop that load on it, it is going to dip and recover. There may even be an overshoot period when it comes back up. The utility will typically not have that problem. So if I have 3 chillers that I'm trying to do, I may want to stagger my 3 chillers by a few seconds or 10 seconds or such, instead of dropping all 3 on a generator at one time, giving a generator time to respond and get back up to rated voltage and frequency. That's what this timer is available to you on, going from normal to emergency. When you look at the time delays, the next one down is the emergency to normal transfer. Usually that leaves the factory at some set point of 30 minutes. By today's emissions, by today's cost of diesel or such, you may want to look at that and say, I have faith in my utility. Once it's back 10 or 15 minutes, 5 to 10 minutes, I'm going to go back. That's an adjustable timer that you have at your disposal. The engine cool down timer, you've run this engine for a period of time, an hour or more. You know, we do this with our car. We simply pull into the driveway and shut the car off. In the case of a generator set, you're going to then unload that generator, and typically that generator will run for about 5 minutes or such unloaded to cool itself down. A point to make on that is I've had calls from technicians that say I've transferred back, but my generator is still running. You have to look to see if there's a 5-minute timer in your generator controller and the 5-minute timer in the transfer switch. You may want to zero one of those out. And then the next one is the generator stabilizing time delays. We've talked about that. When you're doing that, your generator may be able to run all loads connected, but starting everything at one time may be a hardship on it, and specifically your larger equipment loads or those type of loads that can be delayed for a while. This is just a typical picture. If you look on the top, you have a light that says I'm connected to normal or I'm connected to emergency. Those lights will be illuminated, whichever one. Another comment is you'll see in a specification or such that they'll want spare lights. Any of you who have children know those little light bulbs that you screw in type of night light. That was a 6S6 type bulb, and those burned out. All of these new products now are LED type products, and they last the lifetime. So those 2 lights will be there that states what position you are in. The one below obviously says that normal source or emergency source is acceptable. Well, why do I want to know that? Well, I'm still on emergency, but I see my normal source came back. It's past the timer. Why didn't I retransfer? Those are the 2 conditions that I say you may have to pick up an accessory in order to have an additional set of contacts so that you can notify somebody which source is available. The other one here is the test switch. And that test switch, if you move it to the right side, momentarily, it will start your generator, but it will not transfer. Why do I want to do that? Well, I'm just testing to be sure that everything's right. I've done some maintenance. I've done something. I want to be sure everything's back together. My batteries are good, and I need to. I want to just start my generator. If you turn that, and in this case, I said I think it holds for a few seconds or such. Yeah, hold it up for 15 seconds. It will not only start the generator set, it will transfer, and it'll put that into the minimum run timer, and then it'll transfer back to your normal source. You can notice to the left side, there is a bypass. Okay, I'm tired. I proved what I needed to do. You throw it to the left side, it'll transfer and go back to the normal source. So I hope several of these have made sense. I like to hit this point here now. If Nathan is available, I'm right at, according to me, I'm looking like I'm right on the hour. Nathan, do you want to give them a few minutes break?
Yes, we can go ahead and take 5. Let's go ahead and take 5, and we will come back 5 after. 5 after. Thank you.
Thank you. All right, so we're back at it here. And we're going to start the deep dive a little bit more into some of the conditions of a transfer switch. As I stated earlier, you need to know the number of poles, whether it's 3-pole, 4-pole, 2-pole. You need to know the voltage. Now, one thing that's neat is one of the manufacturers, I believe it's Eaton, has put out a transfer switch that will, when you connect it, it will identify what the voltage is. Some of the manufacturers, such as ASCO, you still need to tell me whether you're operating at 240, 208, because we may have a specific controller that needs to be there. The current rating of the transfer switch, and I've been questioned on this a little bit, but the transfer switch needs to be able to carry its capability, whatever it's labeled for, 600, 800 amp. It needs to carry that continuously 24 hours a day, 7 days a week, so on. When you look at a circuit breaker, one of the most common ones is referred to as an 80% rated circuit breaker. And I recently looked up the definition so that I'm not misstating it, but you can only current carry 80%. So if it's a 600 amp breaker, so if you're at a 600 amp breaker, I'm only supposed to carry continuously 480 amps through that circuit breaker. When you look at the definition of the circuit breaker, that period of time that you can draw the full 100%, the full rating, the 600 amps, is limited to about 3 hours or such. There is what's referred to as a 100% rated breaker. I advise you, if it's not making sense, please take a look. It was very easy to Google that and get a little bit better education on it. But in the case of whatever the rating of the overcurrent device, typically a circuit breaker upstream is, if it's a 600 amp, I must have a 600 amp transfer switch. Pushing that point just a minute, sometimes you'll see in the case of some buildings is that it may have an 800 amp service coming in on the normal side. As long as everything is normal, in this case, all elevators are in operation. However, because of the size of the generator set, I'm only going to supply 600 amps, 800 amp from the utility, 600 amp from my emergency generator. I must provide a switch that is equal to whatever the larger circuit breaker is. I can put a smaller breaker, but I cannot put a smaller switch. Just a point of comment. So you look at it here, and you look at, typically we are at 120 to 600 volt. Some of the manufacturers still offer a DC voltage. We are at either 50 or 60 hertz. And in some cases, I can tell you, at least with the 2 or 3 manufacturers I've worked for, if you tell them 50 hertz, they're immediately going to want to know what country are you sending it to, obviously, because there are countries that we should not be doing business with. So when you look at these products, as I've stated a couple of times, anything up to 600 volt is considered a 600 volt product. Let me just touch on that a minute. The next 2 steps are either 5 or 15,000 volt, kV. So if it's 4160, it's a 5 kV. If it's 2300, it's rated 5 kV. In the case of your 15 kV, if it's 12470 or 132 or such, it's a 15 kV type product. So when you move to that with a transfer switch, you move away from that contact that we've looked at several times. And now I am using a circuit breaker. Okay. Now, one point to this is the fact that the circuit breaker is really a dumb device in this regard. It is nothing but a switching mechanism, open, close. Why do I say that so stringently? When you use a medium voltage transfer switch that's using two of these breakers, now you're required to have some type of a protective device, an SEL relay of some type of relay that is going to protect this thing for overload, short circuit, or that type, and also to tell it when to transfer or such. That's a very keen point. You'll also notice that when you look at it on the right side, you see that red phenolic material, and you'll notice those gray pieces. Those are referred to as shutters. The shutters is because Darwin exists. If someone wants to reach in there and shove their hand into those holes with live 15 kV voltage, then you cannot, you have to protect that person from doing something that way. So those are shutters. Many times you are required to have those. The current carrying, continuous inrush, interrupt, overload, and you're back to the withstand and close on rating, okay? So the continuous rating, as I've said a few times, 24/7, both normally emergency position, and no overheating of the contacts. That's one of the things when you look at when you go through the process of getting your UL, you have to look at all those temperature rises, the dielectric and such, and one switch must go through all of those tests from beginning to end. You're not able to use a new switch each time you test. But in this case, and I'll make a comment. You look at the bottom, it says 7 days a week for 20 to 40 years. We still have all kinds of electrical equipment out there that is very much from the 80s and 90s and such and still operating. However, components may not be available anymore. It may be cheaper to replace the switch than to try to go look into a 1985 type switch and upgrade the controller or such. So as quickly as electronics is changing now, yes, we are still required to maintain product with it, but it changes much quicker than it did for a long time. When you look at circuit breakers are broke down into frame sizes. That breaker, the EHJ or the EHD or so, may be good from 50 to 150 amp, from 400 to 600. Transfer switches with many of the manufacturers are broken down the same way. Russell Electric is a little different, unless it's changed recently. All of their switches from 800 amp down was actually the one frame size that they use. Not a critical comment. It's just you have to look at each manufacturer and see where you make these breaks. So in the upper left-hand corner, this is a little modular. What you see is what you get, WYSIWYG. What you see, these are only 30 amp to 230 amp switches. They are a very simple switch, very quickly operated. But when we go back to look at the withstand and close on rating, even at 230 amps, I may be limited to 10,000 amps of fault current. If you're exceeding that amount, you cannot use this product. The next one over to the side is the 260 to 400. That one there may be anywhere in that ampacity range, and typically those switches are good out to about 42,000. 42K fault current. The one below it here, the 600 to 800, that one is good out to 50,000 fault amps. And then the one to the right side there, the 1600 to 3000. And also we make, many of the manufacturers do offer a 4000 amp. Some of those are now even looking all the way up to 5000 amp, which will get away from this contactor design and will utilize a circuit breaker pair to do that 5,000 amp transfer. The point to this is two things. Number one, when you're looking at the correct switch to put into your application, it is not only the ampacity, it is what that fault current could possibly be. The second point is that when you look at transfer switches, and if you are a person that is trying to put that transfer switch into a room, you need to look at every manufacturer that you may be allowing. If you're allowing ASCO, Russell, Zenith, Cummins, and such, you may have to look at it and see the ASCO switch, the Cummins switch may fit, the Russell Electric switch may not. You need to be aware of these breaks, and you need to be aware of the size differences and such. We touched on this earlier. This is a very large version of it, but this is a bypass isolation switch. So looking at it, the bottom portion that you see pulled out, that is actually the 4,000 amp automatic transfer switch, similar to what you're looking at in the upper right-hand corner here up to that 3,000 amp. That is the switch that you see pulled out. The top portion is a manually operated, you can throw those handles and you can connect yourself in parallel to normal or in parallel to utility. And therefore you can then take the transfer switch out without any outage downstream and maintenance it. So the comment, usually twice the size, 2 to 3 times the price. But in the application where it's critical or needed, this is the solution. Another point is we touched on the manual transfer switch pictures a little earlier. That upper portion where you see the 2 handles, that is actually the mechanism now being used, at least by ASCO, as a manual transfer switch. Why do I bring that up? Again, we're back to the convenience stores or something that must have a standby generator, a single generator in the emergency condition. You must have a manual transfer switch with those cam locks. This is more or less that upper portion is the product that you would typically see. Going down into this a little bit later, the interrupting rating. This is what is specified in UL 1008. UL 1008, I believe now is up to the 9th edition, and each one gets a little bit more stringent. But each of these things, in order to be UL 1008 listed, you must pass each one of these criteria. When I tell you that you can use a UL 67 or some other type of product, they are not to this stringency. That's why UL 1008 is specific for emergency systems. Back to the thing that you're going to get tired of hearing me speak about, the withstand and close on rating. An automatic transfer switch connects a critical load to an alternate source. It must be able to withstand a close on. Let's talk about those 2 terms for a minute. A circuit breaker has an AIC rating, an amps interrupting, okay? Its whole purpose is to open. That's it. In the case of a transfer switch, this is where you see not only the term withstand, but you see close on. As we stated earlier, you are going to start that alternative source, whether it's a utility or a backup generator, you're still going to close into that fault because it's still there. The switch must be able to be operated. It cannot fuse together. No linkage can break. It must be usable. We are, as we say, we're requiring the upstream device, the circuit breaker, the fuse to clear us. But the 2 differences is an AIC of a circuit breaker is different than a withstand close on. Many times when you look at plans and specifications, and I hope we don't have any consulting engineers, but I'll make the statement, a consulting engineer may not do his due diligence simply because the transformer at the very beginning where the utility comes in can produce 65,000 amps. As you go through your distribution to your emergency down to that transfer switch, I doubt that down at that transfer switch, you still have the capability of 65,000 amps. We have a little illustration in one of the other presentations that as you do that, we found out that there's really only 10,000 amps that could occur down at a specific transfer switch in the electrical scheme. Why do I bring that up? Why do I want to have to give you oversized transfer switches that condition can never happen? I may have to give you an 800 amp to 1,000 amp switch to do a 100 amp assignment because you have not given me a due diligence, a good number of what you can really have to withstand. Withstand and close on, again, we're talking about the overcurrent device. It causes extreme heat. The way a transfer switch works is the more current you pass through it, the stronger it presses against its contacts. Whereas in a circuit breaker, it will open. In this case, I will sit there and I will continue to press against those contacts. I cannot weld those, and the transfer switch has to be able to still be operated. What does all of this mean? This is what's referred to as an inverse time curve. So if you look on the left side, the number of amps, again, this may be a 600 amp switch, but I'm going to have 25, 30,000 amps instantaneous of a fault current. You will notice that if I'm that high up, I have a very short period of time that I can withstand that without damaging my equipment. As we go across the bottom, all the way out potentially to a 30 cycle, a half second, 30 cycle switch, you can see I'm at a much lower capability. I may be able to withstand 65,000 for 3 cycles. I may only be able to do 30,000, 38,000 if I'm hanging all the way out there for 30 cycles. This is the main point to this whole discussion. So as you look at it, the transformer there comes into the transfer switch, and it depends where that fault current is. If the fault current ends, if the fault occurs where the F2 is, I'm totally relying on that circuit breaker to the left side that says 480, 28, 240. I want that breaker to open. The problem is I'm going to disconnect everything downstream. If I'm downstream where the F1 is, now we get into what's called selective coordination. I want that breaker just above that F1 condition to only open that circuit. Selective coordination in a simple means is if I have a problem with the receptacle in this room, I want that circuit to clear before the whole room would clear, before the whole floor would clear, or before the whole building would clear. Selective coordination. The selective coordination also is why that if your transfer switch is up from the receptacle, the room, and you're all the way up to the building, I may be at 9 to 12 cycles before that breaker is going to clear. That's how you get beyond the 3 cycle rating or such. But this is just where is that fault? And again, if the switch transfers, it is going to close into that fault. And now you're expecting the breaker on the right side to clear. In this case, at least in some of the manufacturers, they will not only give you a circuit breaker that will clear in 0.05 seconds now, 3 cycles, but it may also tell you if you have a specific breaker upstream, we have tested with this breaker, and instead of saying I'm at 35, I am protected out to 40,000 amps, but I must have a specific breaker upstream, okay? The problem with that is you've done your due diligence, you have that breaker in place, and that breaker has a fault. You do not know what breaker they're going to send you from the electrical supply house to put in there. You may no longer be coordinated, and you may not be protected properly. On the left side, I do want you to notice that the fuses, a fuse will clear in usually 4 to 8 milliseconds, okay? The problem, that a good thing with a fuse is that if you have a very large, in excess of 80, 90,000 amps of fault current, and it really is feeding a 100 amp transfer switch. I've had that condition down here in some medical facilities in Texas. If you put the fusing in there, the fusing will protect you up to 100 or 200,000 amps. The deficit to it is the fact that now you have to go out there and you have to replace fuses in lieu of simply resetting a circuit breaker. A molded case circuit breaker is what the MCB stands for. Typically, you see that those will trip in 25 to 33 milliseconds. You notice that a power breaker is one of those larger breakers that may be out there for several cycles. They may close in as much as 60 milliseconds. That's with an instantaneous trip. And then the other one's down below, a power breaker without an instantaneous trip. That's how I'm getting out to 0.5 seconds. I may be passing that fault through for that period of time before that specific breaker will clear. Those are points a little bit maybe over your head, but that's how you get oversized switches when you're looking at an application and say, why did they put this large of a switch in to feed this load? It may be because of these fault conditions. The specific breakers, as I stated before, many of the manufacturers will put a label on there. If you have a good electrical inspector, he will walk up, look at what breaker is protecting this switch on either side. And if it's not on this list, he'll red tag the switch and tell you, no, you cannot apply it with that high of a fault current. You'll also notice that those breakers are broken down in that regard for each, for each type of voltage or such. This is what I was getting to with the comment of selective coordination. If you look on the left side where the fault is all the way down on that bottom, if you are not coordinated, you notice I have taken out all sorts of feeders that I did not need to trip. Okay. Those ones in red unnecessarily tripped. On the right side, and this is what is very difficult when you're doing plans and specs as a consulting engineer, you may have 3, 4, 5 vendors of transfer switches that is looking at 2 to 3 to 4 different vendors of panel boards, switchboards, and such. And at that time, that consulting engineer has no idea what he is going to end up having purchased on this job. Then it's his to go through a coordination study and be sure that he can coordinate things so that only the circuit necessary will clear. Again, as you go up from where that fault is, each of those rungs, that means that that breaker may be 3, 6, 9, 12 cycles out there before the breaker protecting the transfer switch would clear. So in this case, you'll notice verbiage continues to change, but the circuit breaker must include an instantaneous trip in order to apply the 0.5. If you look down below, look at the one that is not in a box. It says short circuit current rating 50 up to 600 volts, and it is saying that that's good for 0.05 seconds. 3 electrical cycles. That used to be called an any breaker rating. That is an instantaneous trip. Any circuit breaker, molded case circuit breaker with an instantaneous trip will clear within 3 electrical cycles. So that's the value, that 50,000 that you need to apply, okay? If you have a long time, what do I mean by that? You look at a circuit breaker, and a circuit breaker has an LSI rating. That's called a long, short, and instantaneous rating, LSI. If you have a short time rating, that's the box below. So that tells me that I can run 36,000 amps through that switch for 18 cycles, 0.3 times 60, 18 cycles. The good inspectors will look at this. If he sees an LSI breaker upstream, he will come to this label and be sure you have a short time rating. Another comment to keep in mind. Standard normal seeking, we've beat to death. That's the one that will go back to the ones, typically utility. In that case, normal seeking is, as we say, it's on normal. We lose it, it transfers and goes to emergency, and then it will return to normal because that is its preferred source. A non-selective, you can choose which one. No preference as to which source is connected to. Why would you have this? Many of the industrial applications may be fed by 2 motor control centers, one from the north side, one from the south side. If the normal center goes down and you transfer to the other one, I don't care. I'll just make it my primary now. I don't need to transfer back. So that may be why you might want to have a non-selective type switch or such in there. Okay. So it is selectable in your case. So in this case, this is a 3-source system, and there are 2 generators with a utility. So in the case, typically, you may have the utility coming in, feeding the load, and then you may have to choose between which generator you want to be the backup. One may be down for maintenance, or you may be alternating them to keep the amount of hours on those correctly. A three-source system simply means, as it shows, utility may be your primary feeding the load, and then you may have a backup to the backup. So that's how a three-source system works. Delay transition switches we have been through. The delay transition switch has a open position. One point I did not touch on, if you are connected to your generator set, and for some reason you start to overload that generator set, maybe a reason why, you have to go into what is referred to as a load shed. And that transfer switch will tell you, get off of emergency. It will open the emergency contact, therefore reducing some of the load on the generator, and the generator should recover. Okay. If you have a standard open transition transfer switch and you load shed, you force the transfer switch off of emergency, the only place it can go back to is to the normal source. If it's gone, you're very fortunate. If it's a brownout, a single phase type condition or so, for that moment, you are feeding your load with that degraded condition. Back to your overcurrent device, protecting it where it should reopen. But as long as you're in the load shed, it will not allow the transfer switch to connect to the emergency condition. When you use a delay transition switch, a center off or neutral position, when you take that load off of the generator, you can go to an open position where neither source is supplying power until you're ready for it to go back to the normal. This is probably a very key point, depending on how critical the downstream load is to some type of a voltage instability. That's one positive to it. In the case of when you're looking at a delay transition switch, a closed transition switch is the same way. There has to be two operators. The upper operator works one set of the contacts. The lower one will move the lower set of contacts. One set of contacts is the normal. One set of contacts is the emergency. The one in the middle is the load coming out, as we've stated before. Delay transition, it allows motors to decay. It does have a mechanical interlock so that you cannot inadvertently do something and close when you don't want to. The off position can be set. Typically, that has to be dictated by someone, typically a consulting engineer or someone that knows the parameters of the downstream load. But I think also in here, one reason that you do not want to have a delay transition switch is that all of the load downstream, when you have a delay transition switch, you may be looking at a motor being on that circuit, but everything that's on that circuit will be without power. And if you have a life safety load or you have a critical load on there, you may not want this to happen. That's one thing to keep in mind. Okay. So the point to this is the fact that when it's correct, you use it. In any emergency system, life safety, any load that needs to be reconnected within 10 seconds, you will never want to put this switch, this design switch in that application. Typically, because you have such a short period of time, you're dropping 1 second to start the generator. And you know, a 450, a 500, 600 kW generator can ramp up very quickly. A 2500, 3000 kW generator, that's a lot of inertia to move within 7 seconds or so. Why do I say 7 seconds? You have to get the start, it has to ramp up, it has to stabilize, and all of that has to happen, including the transfer switch transferring within 10 seconds. The closed transition switch, make before break. Okay. Again, we've touched on that. This is very popular in a lot of research labs. Again, it is there because you just cannot have an outage downstream, depending on your load. As we looked at this before, it will typically overlap somewhere between 20 to 90 milliseconds. At least in Texas, under the Public Utility Commission, the PUC rules, they have what is called momentary overlap. And you have to be on and off within 59 seconds. 1 second. You have to be on and off within 1 second. Okay. If you're on and off in more time than that, now you are under what is called extended parallel, and you may have a whole bunch of more products such as selective relays, protective relays, and such that need to be on here. This switch, when operated properly, will make that transfer within 100 milliseconds and can be proven to the utility company. Again, as I stated before, if you're connected to normal and you close to the emergency and the normal side does not open, it will reopen the last one that you closed. It will reopen the emergency, and there is a relay that will close that will shunt trip that breaker, not allowing it to attempt to go back there, and you need to go see why the switch didn't transfer properly. There is that type of belts and suspenders, type of security that needs to be sometimes presented to the utility company. Closed transition, loads are not disconnected. Okay? These are the parameters. And as I stated a little bit earlier, let's talk about a phrase. One thing that you will hear is that this is a passive synchronizing design. What do I mean by that? I am not doing anything to either source. I am simply sitting there monitoring the source. We're back to my little illustration again with the blinkers on as you're coming to the red light or such. If you watch it, they will blink once or twice exactly right on top of each other, and then they will go out all the way to they are blinking absolutely 180 degrees different. That's what this device is. Passive synchronization. It sits there and looks for this condition. One thing, if you're familiar with a synchroscope and you are looking at that synchroscope going around, and if that synchroscope is moving at a very fast, which means your two sources are very far out of sync, this type of product cannot anticipate it when it's moving that quickly. Most of the time when you connect a generator set, your utility is set usually at 60 hertz. You may set this at 60.1 hertz or so that the generator is running just a little bit faster. Therefore, it will cross within a reasonable period of time, and you will do that safely. That's how a closed transition switch operates. In the advanced class, you will also look into what's called paralleling switchgear. And in that case, we are taking a signal and driving that to the voltage regulator of the generator set. We're sending a signal to the governor to speed it up or slow it down to change the frequency. And we are actually driving those two sources into synchronous and into being synchronous with each other. And therefore, it will close and connect the two sources together. These switches are not. They simply are passively waiting for these conditions to be met. An automatic bypass transfer switch, as we stated earlier, this is a testing of a no load interruption. Let's talk about that for a second. In the case of at least ASCO and a few of the manufacturers, if I am on utility, the only source I can bypass to is emergency. And in doing so, I have no downstream load interruption. Then I can rack the transfer switch out and I can start my emergency generator and I can bypass to emergency. But there are steps that you need to go through. That is referred to as a no load break. No load. One of the other manufacturers, I do know Russ Electric had this switch. It will interrupt the load. But the positive point to it is I can bypass to either source because I'm going to open it momentarily. I can bypass from utility. I can bypass it to the emergency source. Two different philosophies. One is done for emergency, and in our case, we look at it as being under maintenance. But there are steps that you would have to go through. So in this case, you're connected through the transfer switch, and that transfer switch is providing load. Now I add the second set of contacts, that upper portion, the bypass. When I close that, now I have two paths of current. The little V's, the little TP's there mean that that lower unit is a draw out type unit, as we saw in the picture. You can draw that out and no interruption of power downstream because you're bypassed. Those upper contacts, that upper portion is rated again for the identical criteria, amperage and withstand rating. This is once you're in there as a no load break type. That's the transfer switch. It's connected. It's removed. You have three positions. You have connected, where it's obviously in automatic use. You have a test position where you can rack the transfer switch into that portion and you can electrically transfer the switch back and forth to be sure all mechanisms are working correctly without disrupting anything downstream. Okay. And then you can put it completely into the isolated position where you can then remove it, do whatever you need to before you put it back into service. So no load type interruption we've been through here. In the case of many of the manufacturers, you will also notice that it'll tell you that the handles need to be exterior. You do not need to open a compartment to find a handle. The one on the top there, you'll see a little green bullet, however you want to notice that. That tells you which, if you are open, bypass to normal or bypass to emergency. The crank below is how you are racking that blower portion out, and it'll tell you whether you are connected or whether you're in the test position or whether you're in the isolation position. That's what the intention of those two are. So as you do that, you're in the test mode. As I stated, you're sort of disconnected. Your load does not get interrupted, but you are able to transfer that switch back and forth if you've lubricated it or maintenance it of some type. That's that bottom handle layer, and then you turn it to the isolated position, and it is completely removed. The other thing that you might want to know is that, yes, these can be quite heavy. These are typically draw-out construction with the rails. And then what is pointing to there with the yoke or such is the fact that the yoke can be used where you can have sort of like a little jib train or some type of a engine hoist or so, where you can connect the yoke and you can lift it with a device other than by yourself. Automatic bypass transfer switches allows the inspection without any interruption of power downstream. It allows you to test the transfer switch, and it allows manual transfer of the load if power fails when the automatic transfer switch is disconnected from the load and in the isolation mode. We've been through that several times. In this case here, it kind of illustrates it again. Any load? Normal or utility seeking? Yes, a good comment. And everything that you have spoken of, whether it's a transfer switch or a bypass switch, you can get those in either the standard two position, open transition, delay transition, or closed transition. One of the comments still on this slide is a soft load transfer switch. Getting back to the point that I made to you earlier, in all three, the automatic, the delay, and the closed transition, whatever the total load is connected downstream transfers in one amount. When you look at what's referred to as a soft load switch, you will close the generator to the utility and possibly pick up 50 or so kW. And then within a ramp period of time, you will move the load from the utility to the generator at a pace instead of one load being dropped. When you're ready to go back, you will reclose. You will then unload the generator on a ramp speed, and you will put that load back onto the utility. They may have purposes for this. Your generator set may be large enough to run everything, but it does not have the ability to start everything. Another reason may be when you drop all of that load back on a utility, many utilities have what is referred to as a demand charge, a ratchet. And once you hit that demand charge, you may be locked into it for a complete year. So that's what you need to be aware of. Soft load switches are still available. If it's a specific application, contact the manufacturer and see what they can offer to you. I will tell you though, if you're going to put in a soft load transfer switch, the utility company must be contacted. You have to know what their requirements are. To close out in the advanced transfer switch, we'll do a little bit more deep dive into the closed transfer switch. The soft load transfer switch we've sort of touched on. A static transfer switch is SCR driven, silicone relays. What that is that those will typically transfer within 1/4 of a cycle. ASCO no longer manufactures this. That product was spun off when we were sold to Schneider, and the Liebert people offer this transfer switch. Typically, they are in association with UPSs, but it is referred to as a static transfer switch. Service entrance rated transfer switch will be covered. To give you the highlight of that, we will take a transfer switch, and in lieu of relying on the circuit breaker from the utility, we install that breaker. We have the breaker included with our transfer switch. It's called service entrance rated because when you look at normal power coming into the building, whatever it hits first, whatever switchboard or distribution board the utility comes into, that must be labeled service entrance rated, and there must be a means of a single device that opens the power so that if there's a problem where you have to have the fire department come in and start spraying water, they have to know that all utility power has been dropped. If you're putting this transfer switch ahead of that device, ahead of that distribution board, now the first device that the utility hits is our service entrance rated, our transfer switch. Now we are responsible for providing that circuit breaker. So it's sort of a two-compartment, the transfer switch along with the circuit breaker. We'll look into a little bit more modal load transfer. I will tell you that neutral switching is either you have a solid neutral or a switch neutral. If you want to research that a little bit, get into the National Electric Code and look at what is defined as a separately derived source. If I have my utility coming in and at my main gear, I am taking my neutral to ground and making my ground reference there. That gives you the 277 volt off of a 480 volt feed. If I take my generator set and I do the same thing separately out in the yard, I take the neutral, bond it to ground, and drive a ground rod out there. Now I have two references to ground, and I must switch that neutral so that only one source is connected to ground, called a separately derived source, and that is covered in detail in the advanced class. Communication is becoming very critical. Very critical. There's a complete section in the advanced class of communication, but you need to know the distance that I am sending signals to. Is that CAT? Is that CAT5? Is that Ethernet? Is that RS-232 or such? Or do I need to go to fiber? What do you want now to be communicated? One of the other codes that's out there is called the International Building Code, the IBC. And that states that if you are a high-rise building is specified as being 70 feet or more. Why is that? Because that's the highest that a hook and ladder from a fire department can reach, up to 70 feet. If you are a high-rise building and they are instituting the International Building Code, you now have to have remote enunciation of your transfer switches in that fire command room, separate from the remote enunciator that you typically see provided with your generator set. Just a point of contact. And then we'll review this basic module. So that kind of brings me to the end of this presentation. We may have time for some questions. Nathan, if you're back on.
Yes, I'm here. I'm here. Daniel, would you mind typing your email address into the chat box?
Okay. Yeah, let me go back over here. That's fine. Hold on, throw my.
If you have any questions, you could ask them or you could type them into the chat box.
Let's see what I'm gonna do. Where I'm putting this. How do I add that?
Oh, I could just take care of it for you.
Oh, here it is, message.
Oh, okay. Got it?
Yeah, there it is.